Every solar panel you've ever seen is hiding a massive inefficiency. For every photon of high-energy blue light that hits the surface, a huge chunk of that energy is instantly lost as heat. It's a physical limit we've been stuck with for over 60 years. But on March 25, 2026, a paper published in the Journal of the American Chemical Society changed everything. Researchers revealed a molybdenum-based emitter that doesn't just follow the rules of physics, it bends them to its will. This isn't just a small improvement, it's a fundamental shift in how we capture light. By using a process called Singlet fission, this material can turn one single photon into two separate excited states, effectively doubling the potential output of a solar cell. To understand why this is so revolutionary, we have to look at the Shockley-Queisser limit. This is the theoretical speed limit for solar cells, which dictates that a single-junction cell can never be more than about 33% efficient. The problem is one-to-one physics. One photon equals one electron. Any extra energy in that photon is just vibrated away as heat, which actually degrades the panel over time. It's like trying to fill a cup with a fire hose. Most of it just splashes out. But the molybdenum spin-flip emitter changes that. It allows us to reach a quantum yield of 130%. That means for every 100 photons that go in, we get 130 excited states out. It sounds like magic, but it's actually brilliant mechanical engineering at the molecular scale. At the heart of this discovery is a specific molybdenum complex. Molybdenum is a transition metal often used in high-strength steel, but here, its heavy nucleus and unique electron configuration are the keys to the kingdom. The engineering challenge was to create a molecule that could hold onto its energy just long enough to share it with a neighbor. This requires a very specific geometry, where the molybdenum atom is perfectly positioned to facilitate what's known as spin-orbit coupling. And here is the clever part. By tuning the ligands, the arms of the molecule, engineers can control exactly how fast this energy transfer happens. It's like tuning a musical instrument, but instead of sound, they're tuning the flow of quantum states. Before this molybdenum breakthrough, researchers tried using organic molecules like pentacene for singlet fission, but those materials were often unstable, sensitive to oxygen, and difficult to integrate into real-world hardware. Molybdenum offers a much more stable platform. Because it's an inorganic metal complex, it can withstand higher temperatures and more intense radiation. This is the difference between a lab experiment and a product you can actually put on your roof. But even with a better material, the physics of the spin flip remained the biggest hurdle. To get past the 100% limit, the researchers had to find a way to make electrons do something they naturally hate, change their spin direction. This module has set the stage. We know the limit, we know the material, and we know the goal. But how does a single photon actually split into two? To understand that, we have to go inside the singlet fission mechanic. It's a journey into the world of quantum states, where a single moment of impact creates a ripple effect that doubles the energy harvest. It's one of the most elegant solutions in modern engineering. Get ready, because we're about to see how these engineers bypassed a fundamental law of the universe to reach 130% efficiency. The secret is all in the flip. In a standard solar cell, a photon hits an electron and kicks it into a high-energy state called a singlet. This singlet state is like a hot potato. It wants to get rid of its energy as fast as possible, usually by emitting light or heat. But in our molybdenum complex, something different happens. Before that energy can be lost, the singlet state fissions. It splits its energy with a neighboring molecule that was sitting in its ground state. Now you have two excited molecules instead of one. This is the singlet fission mechanic. Think of it like a high-speed car crash, where instead of both cars being destroyed, they both magically turn into two slightly slower cars that keep driving. You've doubled your traffic with the same initial momentum. But there's a catch. Physics usually forbids this split because of spin conservation. Electrons have a property called spin, and in a singlet state, their spins are paired up in a way that makes splitting into two triplets very difficult. This is where the spin flip comes in. The molybdenum atom is so heavy and its magnetic field is so strong that it forces one of the electrons to flip its spin. This spin-orbit coupling acts like a lubricant for the quantum transition. By flipping the spin, the material bypasses the traditional 100% quantum yield limit. It allows the energy to flow into two triplet states that are magnetically allowed to exist separately. This is how we reach that impossible 130% figure. The physical engineering of this emitter is all about distance. If the molybdenum molecules are too far apart, the energy can't jump. If they're too close, they quench each other, killing the reaction. The sweet spot is a distance of about 1 to 2 nanometers. To achieve this, engineers designed a supramolecular scaffold. They used long organic chains to act as spacers, holding the molybdenum centers at the perfect distance, like a precisely engineered 3D crystal lattice. It's a masterpiece of structural engineering at a scale where gravity doesn't matter, but electromagnetic forces are everything. Every bond angle and every spacer length was calculated to maximize the spin flip efficiency. Once the two triplet states are created, they have a remarkably long lifetime, up to several milliseconds. In the world of quantum physics, that's an eternity. Most excited states disappear in nanoseconds. This long lifetime is crucial. It gives the energy enough time to migrate through the crystal structure to the edge of the solar cell, where it can be converted into usable electricity. It's like having a battery built into the light harvesting process. And because we have 2 of these long-lived states for every 1 photon, the chances of capturing that energy are doubled. This is why the molybdenum spin flip is the holy grail of 3rd-generation solar technology. But there was a problem. All of these amazing results were first achieved in a liquid solution, a beaker of solvent where molecules can move freely. But you can't put a bucket of liquid on your roof and call it a solar panel. The transition from liquid to solid is where most breakthroughs die. In a solid, molecules tend to clump together in ways that ruin the spin flip process. They lose their alignment, and the efficiency collapses. Next, we're going to see how engineers solved the solid-state challenge. They had to build a microscopic cage to protect the molybdenum molecules while keeping them perfectly aligned for the spin flip to work. The leap from a liquid beaker to a solid thin film is the ultimate test of engineering. To maintain that 130% yield, the team had to invent a host-guest matrix. They embedded the molybdenum guests into a rigid crystalline host material. This host material acts like a molecular egg carton. It keeps the molybdenum complexes from touching each other, preventing the clumping that would normally kill the spin flip. It's a masterpiece of precision manufacturing. But the host can't just be any material. It has to be transparent to let light through, and it has to have its own energy levels perfectly tuned so it doesn't accidentally steal the energy from the molybdenum. It's a delicate balancing act. Then comes the spin flip interface. For a commercial solar panel, we need to get those 2 triplet states out of the molybdenum and into a semiconductor like silicon. This is where the engineering gets really difficult. The boundary between the molybdenum layer and the silicon layer has to be perfect, down to the atomic level. Any defects or traps at this interface will swallow the electrons, turning our 130% yield back into 0%. Engineers solved this by using a buffer layer, a thin film of specialized molecules that act as a bridge. This bridge allows the spin-flipped energy to slide into the silicon with almost 0 resistance. It's like a quantum slip and slide. Durability is the next big hurdle. Traditional solar panels last 25 years, but high-tech emitters like our molybdenum complex can be sensitive to UV light and moisture. To fix this, engineers turn to atomic layer deposition, or ALD. ALD allows us to coat the entire device in a layer of aluminum oxide that is only a few atoms thick. It's completely transparent, but it's as tough as a diamond, shielding the delicate spin-flip molecules from the environment. This isn't just a coating, it's a structural component that keeps the entire molecular scaffold under the correct pressure to maintain its spin-flip properties. It's engineering at the limit of what's physically possible. So, what does a world with 130% quantum yield look like? It means solar panels that are significantly smaller but produce the same power. It means electric cars with enough rooftop solar to actually charge themselves while driving. It means the Shockley-Queisser limit, which has defined the energy industry for decades, is no longer the ceiling. We are moving into the era of multi-exciton solar, where 1 photon is just the beginning of the story. The engineering behind this molybdenum emitter is a testament to human ingenuity. We took a heavy metal from the steel industry and used it to rewrite the rules of quantum physics. Next time you look at a solar panel, remember that there is a hidden world of spins and flips happening just beneath the surface. The journey from a single photon to a double electron is one of the most incredible feats of modern engineering. We've gone from understanding the problem to building the solution, atom by atom. The molybdenum spin flip isn't just a discovery, it's a bridge to a truly sustainable future. And the best part? We're just getting started. Because once you know how to flip the spin, the possibilities are limitless. I'm Ada, and this is how we're engineering the future.